nice thing about actually this is I have an editor that can clip out all of what I'm doing right now.
Oh, okay, so you're good.
Yeah, I'm chilling. So this is our concept right here. This is what the system in residential homes currently look like with a ground source heat pump. We removed the ground source heat pump, that would roughly be right here, to show a simplified loop to explain our concept. Basically, the ground source heat pump pumps the water through the ground as a cold water, which the ground heats up the water and preheats it, and then it comes over through the ground source heat pump into our hot water storage tank. This is our domestic hot water through a closed pipe and heats it. On the other side, our HVAC system for a home usually involves an air conditioning unit and a furnace with a refrigerant loop in between. So the cold refrigerant will get cooled by the air conditioning unit, come through, allow the cold air to come through. This is obviously during summer. And then that warm refrigerant will come back and then go get cooled by the ACU. What we're thinking about doing is taking an additional heat exchanger and placing it here. Okay. So what we've done here is we've added this heat exchanger. What we've done is we've taken our domestic water loop and we put it through this heat exchanger and then continued on. And we've taken our warm refrigerant from our furnace and ran it through there as well. So what this does is it allows us to preheat our water going through this loop, which increases energy effectiveness. However, we need to add two different valves on the supply side of this heat exchanger. The reason why is if the heat exchanger is ineffective to run, we have a bypass valve, so that way it can just run as a normal loop. So our two paths for each of our things is we have the warm refrigerant coming out, down, over, into the heat exchanger, back out after transferring some of its heat and continuing, or out, down, over, bypass the heat exchanger and continue on a normal loop. The same is done for this domestic water. It can either come through, up to the heat exchanger and out, or just go straight through on its regular loop.
So the reason why we did our proof of concept as a controller is we need to be able to control that valve. And so our effective ranges for when we are going to be using our heat exchanger is 17 to 90 degrees, because that's when we will want to use our heat exchanger to transfer energy to our water loop. And so when we are not within our effective energy range, we are going to bypass the standard operation if we are within 0 degrees Celsius to 17 degrees Celsius. So then if we are not within these ranges and we are at freezing or boiling for our water, we will have our warning light come on so that we do not freeze or boil our water within the system.
So this is our code that runs our logic center. We can see here that it's a very simple code, very short, but what it does is it plugs out our temperature. So right now, our temperature sensor is running right about 14 degrees Celsius in this jar of cold water. And here's our setup.
Okay. So for our setup, we are using an Arduino ESP32 as a control sensor, and this control sensor will have the logic depending on our certain temperature thresholds for our piping to be able to change from blue cold, red is hot water, and then our yellow is domestic. So when our temperature threshold is greater than 17 degrees C, it will flip to a red light. As we can see here, we take the temperature sensor out of the water, the cold water, and put it in the hot, and then when it reaches that temp, it will flip to our red. And
this demonstrates that when the refrigerant piping from our concept reaches a temperature that is effective for heat transfer, it opens the valve, allowing the refrigerant to operate the heat exchanger for the energy recovery.
Then our failure criterion is when we are below freezing, our failure will turn on. Or if we are above 90 degrees Celsius, our failure will turn on. Or if the temperature sensor cannot get a reading. And then,
for example,
if it cannot get a reading, it will show yellow as failure.
And this will turn off the system to avoid any accidents within a residential home. So the two things we've learned from this prototype design of our concept was first off, we need a pressure release valve on our refrigerant loop, because if we hit our warning areas and we need to bypass our heat exchanger, that heat is just going to be cycling through our system. And if our ACU can't handle that, we need some way to be able to release that temperature and pressure so we don't have a failure. In addition, we were realizing that the temperature sensor that we have takes time to be able to process what temperature it's reading. So if we have a refrigerant loop that is increasing temperature very rapidly, it takes a little bit before our sensor actually recognizes that the temperature is growing at that rate. And so we think we need to adjust our temperature ranges for the warnings to be able to give ourselves more time and more of a safety factor when operating our system.